I'd like to welcome everybody to the Mars track for the second day. My name is Andreas, and I'm going to be chairing the track today. Let's go ahead and get started. We're going to have the first speaker is for 1 hour, and then we'll have about 10 minutes at the end for question and answers. Our first speaker is Dr. Robert Braun. He is an associate professor in the Guggenheim School of Aerospace Engineering at the Georgia Institute of Technology. As director of Georgia Tech's Space Systems Design Laboratory, he leads a research program focused on the design of advanced flight systems and technologies for planetary exploration. Prior to coming to Georgia Tech, Dr. Braun worked at NASA Langley Research Center for 16 years, where he contributed to the design, development, test, and operation of several robotic flight systems. Dr. Braun is the principal co-author or author of over 100 technical publications in the fields of planetary exploration, atmospheric entry, multidisciplinary design optimization, and systems engineering. Please help me welcome Dr. Robert Braun, presenting Entry, Descent, and Landing Challenges to Enable Human Mars Exploration.
Thank you very much. Thank you. Let's see. All right. Can you hear me okay? Hear me in the back all right? Is that better? Good. Good. First of all, let me start out by just asking a question. How many people in the room here think the United States should be spending time and energy to send humans to Mars? Just raise your hand. It's a good session. But wait, put your hands up for a second again. If you think we should be spending time and energy to send humans to Mars, great. Is your hand up? Okay. All right, now how many people, keep your hand up if you want to go yourself. Ooh, I got a lot of brave people here today. I've been thinking about this a lot. I've actually been thinking about it for the better part of 20 years. I am a hardcore believer that the United States should be spending time and energy, effort, whatever it takes to be planning to send humans to Mars one day. I'm not so sure I want to go myself. It's a long way. Just the flight here to Dallas was, kind of long for me. But I do think it's an excellent goal for the United States, and it's something that I've been very privileged to contribute to over a couple decades. What I want to talk to you about today is, in my opinion, one of the chief problems, one of the chief challenges with doing just that. There are, of course, a number of engineering challenges with sending humans to Mars. Things like all the mass you have to lift on big launch vehicles to get there. Things like habitats you have to build and environmental life support systems you have to build. But there are only, in my mind, there are only a couple of challenges that rise above the others. Challenges that we actually don't know how to solve today. We don't know without maybe a miracle or two occurring along the way. And this is one of them. Basically, entry, descent, and landing. So that's what I'm going to talk about. Before I continue, I want to mention my co-author, Rob Manning at the Jet Propulsion Laboratory. Rob and I have collaborated off and on this subject for a while. Some of these charts are his, some are mine. It's kind of a mixed bag. Of course, any mistakes, anything I say wrong is, of course, my fault. Okay, so what I'm going to do is I'm going to talk to you a little bit about the Moon, Earth, and Mars, and why it's true that it's so hard to land on Mars. I'm going to tell you what we've done so far in terms of our robotic program, because our robotic program has been very successful at landing small masses on Mars. And then I'm going to kind of extrapolate what that means to the scale of human Mars exploration. I'll throw out some possibilities for things that might work to solve this problem, and then I'll show you some overall concepts to do the whole mission. And then, of course, hopefully there'll be plenty of time for questions at the end. Okay, so what's the big deal? Why am I up here today saying it's so hard to land on Mars? I mean, it seems kind of ridiculous, right? We land big things on the Moon. We land big things on the Earth. We've landed on Mars. Well, let's take a look at that a little bit closer. The Moon has a low gravity environment and it has no atmosphere, right? But we've landed pretty big things. The Apollo missions, 16 or so metric tons. Robotically, we've landed a couple of metric tons, the Russians have at least. So you know that can be done, and you know that NASA today is planning on landing even more and more mass on the Moon. So from an engineering perspective, landing big things on the Moon is probably possible. On the other end of the spectrum, we have the Earth. The moon has no atmosphere. The Earth has a very respectable atmosphere, thankfully, for all of us here today. It's a fairly thick atmosphere that allows us to use drag and slow down. The Earth also has more gravity, of course, than the moon. Gravity goes into velocity, which is why I'm talking about gravity. It goes into the speed that you enter the planet. And of course, we have a lot of experience landing heavy things on the Earth. The Apollo program did it. Whenever we bring the space shuttle back, it is an engineering marvel. It's on the order of 100 metric tons of stuff. It's on the order, the space shuttle orbiter is on the order of the mass of the payload only that we want to take to Mars, okay, and land on Mars. So what's the big deal? You see a picture of the Spirit landing site on the bottom of this slide. And Mars is kind of in between the Earth and the moon, right? It has 3/8 the gravity of the Earth's, and it has some atmosphere, about 1/100th the atmosphere of the Earth. So it's in between. If we can do the two boundary conditions, why can't we land heavy masses on Mars? Well, that's what we're going to talk about today. And if I had to sum it all up, what I would say is I love the Mars atmosphere and I hate the Mars atmosphere at the same time. The Mars atmosphere is a harsh mistress. It's too thick to land like we do on the moon. Because there is an atmosphere, there is drag and there is aerodynamic heating and things like that. So we can't just land a propulsive stage on Mars. We have to deal with heating and winds and density variations and dust in the atmosphere that changes the design conditions, right? It's there. On the other hand, it's so thin. Think back to my initial title slide, which was a Viking orbiter picture of Mars, where you could actually see right through the thin Mars atmosphere. It's so thin that sea level density, if there is such a thing, on Mars, is about 1% of that on the Earth. In other words, imagine trying to land the space shuttle on a runway at 100,000 feet here on the Earth. That's what we need to do to land that kind of mass on Mars. In your head, you know that's a very difficult proposition. So that's why I'm upset about the atmosphere. That's why the atmosphere keeps me up at night. On the other hand, I am very thankful that Mars has an atmosphere. Using the drag that you get by flying through the atmosphere, we can save all kinds of mass. It's a great gear ratio, if you will, in reducing the amount of mass we need to start with in a human Mars exploration mission. If we didn't have the atmosphere at all, and we tried to propulsively land on Mars like we did in the Apollo missions, for every 1,000 kilograms, every 1 metric ton of payload that we tried to deliver to the Mars surface, we'd have to start off with 70 metric tons in low Earth orbit. That's a lot of mass in low Earth orbit, right? Remember, we want to land something on the order of 100 metric tons, okay? Now, if we use propulsion to get us there, and then we allow the atmosphere to slow us down, and we somehow figure out how to deal with the craziness of the density variations and the heating and the drag, well then, for every 1 metric ton of payload we want to land on the surface of Mars, we only need about 5 or 6 to start with in low Earth orbit. It's about a factor of 10 there, improvement, because that atmosphere is there. So that's why I'm thankful for the atmosphere. And we use that, by the way, we use that ratio every day when we send robotic probes to Mars, as we have done successfully. And so the question that I want to try to tackle today is, will this same thing work for human missions? In my opinion, and there have been a lot of studies published on what things look like as they fly through the atmosphere in Mars to land humans there in the future. In my opinion, all of those studies are good. They're all close to being right. But they tend to require a miracle or two along the way. They tend to magically require a parachute that deploys at Mach 5, or a big propulsion system that doesn't weigh anything, or things like that. And I'll talk about some of that today. In my opinion, we do not actually have a completely, from a technical point of view, a complete feasible way without any miracles of accomplishing that job. There are lots of ideas and there are lots of technologies that we can use, and I'm going to talk about those today. But what we need to do is develop some of these technologies that haven't been proven yet, prove them out, and then I will believe that we can send humans to Mars. And I believe we're not that far from doing that. Just graphically, I'm not going to go through all this data here, but just graphically on this slide, I have some pictures for you. This plot in the upper left shows the density of Earth and Mars. You can barely see the Mars atmospheric density. It's not a log scale. It would be a little easier to see on a log scale, but it gives you an idea for what I'm talking about, the thinness of the Mars atmosphere. In the top right here are a couple of trajectories. A trajectory returning to the Earth from the Moon, from low Earth orbit, is shown in blue, and a trajectory at Mars is shown in red. The trajectory of the Earth vehicle is much, much heavier. The vehicle in that trajectory is much heavier than the Mars vehicle. Still, the Mars trajectory decelerates. This is altitude versus velocity. The Mars vehicle decelerates much lower in the atmosphere. The reason for that? We got no density, right? The vehicle's basically falling, trying to find the density regime where it's thick enough to slow down. You can see that most of this deceleration, and by the way, this is a robotic mission. This is the Mars Science Laboratory. Most of this deceleration is occurring 20, 30 kilometers above the ground. You don't get to Mach 1 in this case until you're maybe 10 kilometers above the ground. That doesn't give you very much time to do all the other things you have to do. Drop your heat shield, find the ground with the radar, turn your propulsion system on, slow down to reach the ground safely. What's shown in the bottom slides is kind of the result of these trajectories. Basically, this is terminal velocity, the velocity that you would reach in equilibrium just from drag and gravity on the Earth and the Moon and Mars. And what you see plotted as a function of altitude, and essentially this is mass. This is a measure of mass. It's called ballistic coefficient, which is mass divided by drag area. But what you see is this color here is a subsonic terminal descent, meaning like these are velocities that a skydiver might achieve, right? And you achieve these velocities at Earth very high, 20, 30 kilometers up. When the Stardust capsule returned from space, when the Genesis capsule returned from space, they deployed parachutes about 35 kilometers above the Earth's surface. Look over here on Mars. This is supersonic conditions. This is about Mach 1, and this is subsonic conditions. For some conditions, it's actually not possible to achieve subsonic speeds high on Mars. So now we need a whole different approach, right? We need an approach to supersonic deceleration as we approach the ground. So why is aero assist important? It's kind of summarized on this slide that I borrowed from some friends at the Johnson Space Center. This is from one of their human Mars studies showing the mass required in low Earth orbit to begin the mission. By the way, these are in units of space station mass. Once it's fully assembled, by the way. We're not quite at 1 yet. And you can see that for a standard mission that uses all chemical propulsion without any entry at both Mars and Earth, it takes about 8 space stations of mass to accomplish the JSC mission objectives. On the other hand, if you use aero assist, if you go through the atmosphere of Mars and use its incredibly thin atmosphere to help slow you down, you can cut that right in half. Okay, and that's the beauty and the pain of the Mars atmosphere. Now, what have we done so far? We've been very successful. The United States has been extremely successful, but we've been successful at a different problem. We've been successful at sending very small, low-mass robotic payloads to low-elevation sites on Mars. This is a MOLA map of Mars that I'm sure many of you have seen. Light blue is low and the red is high areas. And we have landed successfully 5 times on Mars. 1, 2, 3, 4, 5. The 2 Viking landers in '76, the Mars Pathfinder mission in 1997, and the 2 MER rovers that are still going strong today. And that's a fairly good record, actually. We've only had a few, the United States has only had a few robotic failures. But what does that tell us about Mars? Well, all of 5 of these missions, the maximum mass, the maximum landed mass, not usable payload mass, but the maximum mass that we actually touched the surface with, was 600 kilograms, 0.6 metric tons. Okay? And they all landed, look at this, they all landed in the lowlands. minus 1.4 kilometers below, let's say, a reference sea level. Well, I mean, do we want to send humans there to the bottom of the planet, or we want to send them to maybe a 0 kilometer elevation or a 2 kilometer elevation? Think about how fast density is going to go away as we move that surface elevation up. Okay. Lastly, they all landed in these huge footprints. Basically, each footprint was on the order of 100 kilometers in extent. And we didn't know precisely where it was going to land within that region. These things, these three numbers, are all challenges for human exploration, right? We need more mass. We might want to go to a higher elevation site, but we certainly need more precision if we're going to link up with a cargo mission that's gone in advance, or if we're going to break our ship into multiple ships and have them rendezvous on the surface. This 100-kilometer thing just won't cut it. And so that's why I'm trying to tell you we've been very successful, but humans on Mars is a whole new ballgame. Now I want to finish off with the robotic missions. I want to tell you that the robotic program is still going strong, and we have a couple of really great missions in the queue. Actually launching in 2 months, we have the Phoenix lander, which is going to only send 167 kilograms, 0.16 metric tons, of payload to an extremely low site, but it's going to do a really neat science mission near the North Pole of Mars. And a few years after that, we're going to send the most challenging robotic mission to date, almost 1 metric ton. We're really getting there, right? Almost 1 metric ton of payload, 850 kilograms to plus 1 kilometers on the surface of Mars, and that's called the Mars Science Laboratory. Both of those missions are in development, and they're both employing technologies that we believe will work and that we could extend a little bit, but the technologies of these missions won't extend far enough to allow us to do human Mars exploration. Now, why is that? Well, take a look at the design reference missions that NASA has done over the last couple decades. There's Mars DRM, Design Reference Mission 1, and Design Reference Mission 3. Design Reference Mission 1 called for 65 metric tons of payload. Not 0.65 metric tons, like we've done today, but 65. Design Reference Mission 3, they skinnied it down a little bit. I guess they sent smaller astronauts, and they got it down to 45 metric tons. Okay? So I don't know exactly what the payload mass requirements are for human exploration, but the number that I keep in my head is that we need to land something like 20 to 100 metric tons to make this feasible. I say 20 because if we really needed 100, maybe we could break it up into pieces. Maybe that would be something we might want to study. But regardless of whether it's 20 or 100, it's a big difference between those numbers and 0.6. Okay? Now, even if you scale it to the Apollo mission, which in my mind is one of the greatest human exploration accomplishments of all time, the Apollo lander landed on the order 10 or 15, 10 or 15 metric tons of stuff, of mission equipment on the moon. Even that is small in comparison to what we're talking about Mars. And if you look at the pictures, if you look at these drawings, engineering drawings that have been done, take a look at the size of that huge Apollo lander that you see in like the National Air and Space Museum, for instance. Can we really land something this big? These are 2-story houses. Can we land one 2-story house, by the way, with a nice SUV, right next to another 2-story house? Can we land them close enough to each other that those two neighbors can reach out, shake hands, connect the plumbing for the cargo mission, that sort of thing? It looks good in view graphs, okay? And it is possible. But this is a real challenge, right? Look how small that Apollo lunar lander looks next to the type of stuff we need to send to Mars. Okay, so where are we now? Well, one thing I will tell you is that we had a tremendous technology development program in the late 60s and early 70s that, among other things, led to the Viking Mars missions. And the Viking Mars missions gave us all kinds of new technologies. We have used those technologies over and over and over again since, and we really haven't developed much new. This is something I think that is a big shame. And you can see that across all of our robotic missions. So here's the Viking missions, Mars Pathfinder, the MER missions. the Phoenix mission that's going to go later this summer, launch later this summer, and Mars Science Laboratory. And yeah, the aeroshells, they get a little bigger. Sometimes they fly at an angle of attack and generate some lift. But in general, these are all 70-degree sphere cone, blunt body aeroshells. By the way, the CEV is not dramatically different than this. They're all 70-degree sphere cones. They were developed as part of the Viking program, and we have used them ever since. It turns out that the Mars Science Laboratory, which is taking almost 1 metric ton, may be pushing the limit of the 70-degree sphere cone because of how much stuff we can put inside of it and because of the heating that it encounters as you try to put more and more mass in here. Okay? So we've done this at least 5 times. On the robotic program side, we are taking big steps forward. MSL is really going to push the envelope of our Viking era technology by allowing us to land a bigger rover, which, by the way, requires us to deliver about 3 metric tons to Mars. There's a payload fraction here, by the way, of about 28%. It's a number to kind of keep in your head. However much mass you deliver to the top of the Mars atmosphere, you can have about 25% of that be useful payload. Right? That's about as good as we've been able to demonstrate in the robotic program. However, the next step is across an ocean. And in my opinion, eventually when we get there, the way we do entry, descent, and landing for human missions will be very different. It will be different. This is a bunch of words that I'm going to skip over. It'll be different because these technologies, the 70-degree sphere cone, the SLA 561V thermal protection system material, the supersonic disk gap band parachute, and the propulsion system that we use on today's robotic missions do not scale beyond about 1 metric ton of payload. MSL is taking them to the limits, and the limits are defined by things like altitude, because we don't want to hit the ground before we deploy the parachute. Defined by timeline, right? We have all these events that have to occur, so there's a certain amount of time involved. The aeroshell diameter, packaging volume, and the way that we prove these things will work, verification and validation approaches. So all of these things are limits on these technologies that will require new solutions for us to do human Mars exploration. Now let me show you that graphically. Okay. This is just a trajectory plot, and I'm going to show you quite a few of these. This is altitude versus velocity. These velocities, by the way, are all very low. So this is about Mach 3. So you enter way over here up in the upper corner of the room, and you come down and you decelerate all the way down here to Mach 3. So I'm going to zoom in on the last little portion of the entry, descent, and landing phase. And the way we do our missions now is we deploy a Viking-era supersonic disk gap band parachute. Those parachutes have been proven useful from about Mach 2.1 to about Mach 1.3, 1.2. They have to deploy above a certain altitude because of all the other things that have to happen after you deploy the parachute, right? You don't want to deploy it right above the ground because you won't have time to drop your heat shield and find the surface and that sort of thing. But as long as we deploy in this region, we're good to go with a Mars mission today that uses a parachute. Similarly, if we want to use a subsonic parachute or if we want to use propulsion, we have to get in these boxes on the altitude velocity trade space. Okay. Now what's shown here is an MSL trajectory. And by the way, if you did not deploy the parachute on MSL, the Mars Science Laboratory, the little 850 kilogram rover, and you continued along that trajectory, you would hit the ground supersonically. Okay? So a parachute for MSL is absolutely needed. Well, as mass goes up, what do you think happens to this trajectory? It comes down. Actually, before I show you that, let me show you that the Earth-Mars comparison that we were talking about earlier. This is another way to view the problem, the difference between Earth and Mars. If you take those same boxes, the parachute region, supersonic parachute, the subsonic parachute, and the subsonic propulsion region, and you show them on Mars versus Earth, see how much higher they occur on the Earth? That's a good thing. That's called margin, and that's very important when you're designing challenging systems. Right, this, by the way, is a larger portion of that trajectory phase plot. Now, the past robotic missions, all of them, Viking, Pathfinder, MER, Phoenix, MSL, I have all the trajectories on here. And now I've expanded this box so it starts up at 60 kilometers altitude and it starts at a very high speed, 7 kilometers per second on the x-axis. And you can see what happens. They all fly in here and they all hit the supersonic region, right? Because we deploy supersonic disk gap band parachutes. And then they go straight across with the parachute deceleration into the propulsion box, and they propulsively decelerate to the surface, right? That's great for the robotic missions. But what about future Mars missions, future human exploration missions? What you'll see is that as the mass goes up, I could take that original plot, which is shown here, and as the mass goes up, I come down on this plot. As the mass divided by area goes up, these trajectories go up, okay? And so what you see here is in ballistic coefficient, which remember is mass divided by drag area, is somewhere around a ballistic coefficient of 150 kilograms per meter squared. This parachute's useless to me. It won't work. It won't actually inflate. Or at least I haven't proven that it will inflate. Let's put it that way, right? This guy here, this ballistic coefficient of 200, he's going to hit the ground at Mach 1.5. That's, I need to come up with some new technology that's going to decelerate me in this region. Maybe I need to extend this way. Maybe I need to push the trajectory up by going to larger and larger aeroshells, right? This has got mass in the numerator and area in the denominator. So if I go to larger aeroshells, I'll go up. And there are a number of concepts that I'll talk about that do just that. Okay, so as mass grows, our ballistic coefficient increases. And when it gets above about 150 kilograms per meter squared, which, by the way, none of the robotic missions have had to deal with yet, our Viking heritage, our big technology program from the 70s, breaks down, and we need new technology. Without some significant modification, we can't do these missions of the future. Okay? One alternative that I mentioned would be to decrease ballistic coefficient by making the area larger, and I'll show you an example of that in just a minute. And there are other options as well. So let's say our aeroshell is no longer a 70-degree sphere cone. Let's say it's just a big inflatable kind of thin film structural device, very lightweight but large. Maybe it's 30 to 40 meters in diameter, right? Now, I'm way up there in ballistic coefficient. In fact, here's my supersonic parachute box. I don't even have to worry about that thing. I don't need a parachute. I can ride this thing all the way down to the ground, to my subsonic propulsion. So that's great. That's a great technology. Can we do it today? I'm not sure. We've never flown anything of this size, flight tested, anything like that. There are going to be this is going to have to be very lightweight, so there's going to be some material challenges, yet it's still going to have to go through somewhat of a heating environment, okay? And in addition, think about the density perturbations and the wind blowing this thing around. I'm going to need some sort of control to make sure I land in the right spot with a concept like this. Yeah, on paper, it's feasible, but in reality, there's a lot of work to be done on this concept. I could also go the other way. I could try to take that parachute box and I could do more testing. Maybe I could extend it up to Mach 3 instead of Mach 2.1. That is certainly possible. Those tests are very expensive, though. They have to be done here on the Earth at 100,000 feet with a high-altitude balloon and a rocket. It can be done, but it's difficult. It's something the robotic program could probably get a lot of benefit out of, because maybe we go from 20-meter chutes to 30-meter diameter chutes. But to be honest, the parachute is not going to cut it for human Mars exploration, because the parachute for a 100-metric-ton vehicle would have to be so big that it would take longer to inflate than you have before you reach the ground. Clusters of parachutes also have a similar problem. So yes, you can extend the box of that parachute deployment region, but in the end, once you start talking about masses over 20 metric tons, in my opinion, parachutes are a dead-end technology for this application. So what we need is a new supersonic decelerator. Maybe instead of taking that inflatable, that large 30 to 40 meter device through the hypersonic pulse, maybe we just take a capsule through the hypersonic pulse. And then when we get down to maybe Mach 5 or something, instead of deploying a parachute, we could inflate our thin film drag device there when it's beyond the big heat pulse. That might work, actually. Another thing we could do is we could use on-orbit assembly, of course, and make our aeroshells just bigger. That would work as well. Okay. So here are some concepts, by the way, that people have proposed for just that. These are inflatable devices that deploy, possibly around Mach 5. This one here deploys out in space and is used, through the hypersonic pulse. But these others are kind of first step concepts that might take us in that direction, but take care of the supersonic problem only and let the heat shields and the capsules still worry about the hypersonic problem. Another concept that people always want to throw out at me is lift. Well, the reason it won't work is because those 70-degree blunt bodies, they just decelerate with drag. Why don't we fly the space shuttle? The space shuttle has a high lift-to-drag ratio, L over D around 1 hypersonically. Maybe that would help. Yes, lift helps. That is true. And what I've shown here are different amounts of lift-to-drag ratio going from 0.2 to 0.5. And it goes something like, you get about 100 kilograms per meter squared in ballistic coefficient for every 10th of L over D. So I told you before that the limit was about 150 kilograms per meter squared for a ballistic vehicle. If we have an L over D of about 0.3, we can get that up to 300 kilograms per meter squared. We can make some improvements with lift, that is true. The thing to be careful of, though, is when you get more lift, the way you get a higher L over D usually is not by getting more lift, but by getting less drag, right? Because it's the ratio of the two. Well, less drag is what we don't want, right? Remember, it's a very thin atmosphere, and we need all the drag we can get. So what we need are vehicles that produce a lot of drag and some lift, a modest amount of lift. Maybe more than the current vehicles, but probably not as much as the space shuttle does, right? Now let me talk about one problem that has risen kind of above the others, at least in my mind. When you design a human mission, and there are some slender body concepts that look something like this. This is called the ellipse sled. It's a NASA Johnson Space Center concept that they've been looking at. It's basically just a slender body that fits on top of the launch vehicle well. And if you were to fly the ellipse sled in at Mars, it comes down like this, and it misses this box. If you go back to the DRM-3, by the way, they flew an ellipse sled, and right around here they deployed a parachute. I'm not sure how. But they did. They deployed actually a cluster of 3 50-meter diameter parachutes, and they landed in their concept study. This issue of how this vehicle closes, how you can take a vehicle like this and somehow decelerate through the supersonic regime, is what I call the supersonic transition gap, or the supersonic transition challenge. And it is probably maybe our biggest problem in landing large payloads to Mars. You just can't move this guy over, and you can't extend this box all the way over here to Mach 5, right? So what might we do? Well, let me describe the gap first. The gap is below Mach 5, and it is affecting the delivery capability of large entry systems to land on Mars. The current supersonic and subsonic decelerator technologies just won't work. We have to get across this gap because we have to get subsonic so that we can drop the heat shield. We have to drop the heat shield because the radar has to see the ground. The radar has to see the ground in time to do propulsive descent, which today is done entirely subsonically. Okay? All of these events are done below Mach 0.8 today in the robotic program. All of our test program, all of our analysis program is geared towards subsonic happening of these events. What we need is to either figure out a way to cross this gap or to initiate these events supersonically. Somehow drop a heat shield at Mach 5, or have the engines come out through the heat shield at Mach 5 and still work. Somehow have a radar work through the heat shield at Mach 5 and find the ground. Okay? Well, in other words, what we really need to do is go from flying this way in a slender body at Mach 5 to coming down and landing. Doesn't sound that hard, but we have to do it in about 90 seconds. And that does make it challenging. Because in this 90 seconds, we have to go from Mach 5 to subsonic. We usually have to drop stuff. We have to undress the vehicle, reorient the vehicle from one attitude to another. We probably have to translate over to our safe landing site or to where the cargo is. We have to do all of those things before hitting the ground. And remember, for our discussion today, the ground is at 100,000 feet. It's not here in Dallas. If we were on the Earth, the ground is at 100,000 feet. And that's the real challenge, right? Getting all these things done with a surface assumed to be that high in density altitude. So those are the technical challenges. There are a whole bunch of others, by the way, that I really just don't have time to cover. I've mentioned a few of them, and I will cover one or two more. Things like landing accuracy as a challenge. I've talked about the need for maybe bigger and bigger aeroshells, maybe new thermal protection system materials, a better way to package our vehicles. We really have a hard time getting all the stuff we want to take to Mars inside one of these vehicles. If we're really going to send humans to Mars, it might make sense to send them into orbit first, wait out a dust storm if there is one, have them do reconnaissance from orbit before going to the ground. Well, there's a technique called aero capture, where you can fly through the atmosphere and decelerate just enough to capture into orbit. And then, from orbit, you could do entry, descent, and landing down to the ground. Boy, it would be great if we could use the same devices to do both of those things. Today, not possible. In the future, maybe. I really actually think this one is going to be solved in the future. Of course, there are big mass problems, big mass fraction problems, and I've already talked about this supersonic gap issue that might require us to develop propulsion systems that initiate at Mach 5 or around Mach 5. And of course, if there are going to be humans involved, we have to do a much better job than we do in the robotic program from a risk and reliability perspective. You know, we do take a moderate amount of risk with our robotic missions. So let me talk about a couple of those challenges just a little bit more to kind of round out the discussion. This is a picture of Gusev Crater, where the Spirit rover landed. And this is the Mars Pathfinder footprint. It was actually about 300 kilometers in dimension, in major axis. And what you could see is we couldn't send Mars Pathfinder to Gusev Crater because the ellipse is just too big. We had not enough control authority of it. Well, future missions, like the MER missions, robotic missions, have been able to land here. So you know that today what we're doing is we're landing with about a 100-kilometer footprint. That's not going to be good enough for humans. We probably need to get down to maybe 100 meters, I would guess. We probably want to land our human mission maybe a football field away from the cargo ship. Probably not much more than that, I would think. Right? And to do so requires a lot of things. It requires maybe a little bit more lift. It requires some propulsion to maneuver around. It requires an autonomous guidance and control system to look at the terrain and compare the terrain with an onboard map, figure out where we are, and fly to the right spot. It requires a number of things. By the way, we can do some of these things now. It's really actually exciting. These are some MRO images, Mars Reconnaissance Orbiter, and you might have seen these on the internet or in the news. These are images that we actually took from orbit of the Opportunity rover. You could see the rover in these images, maybe not on this particular image because of the way I have it projected. But if you have the real image, you can see the rover. In fact, you can see the mast on the rover and the shadow it creates. Okay? That's amazing to me. Let me tell you why that's amazing. Well, first of all, it's kind of cool. But it's also amazing because that means I can see rocks. Right? I want to see the rocks on Mars before I send the humans there. In fact, what we're doing for the Phoenix mission, the one that's launching in a couple months, Phoenix is landing on legs that happen to be a little bit fragile to rocks. And we're scouring the Phoenix landing site, and we're mapping all the rocks greater than 1 meter in diameter from orbit ahead of time. And then what we're going to do is we're going to place these big 100-kilometer ellipses where there are no rocks, or where there are a minimum number of rocks greater than 1 meter in diameter. This is a fantastic capability. This is something we've never had before. This is proving the way for human exploration. We desperately need this. Now, if it was human exploration, and these ellipses, by the way, the colors here indicate, the color in the background indicates the number of rocks greater than 1 meter. Purple is almost none. Okay, just so you know. Now imagine if this was human Mars exploration and we were putting down 100-meter footprints. I could easily find 100 meters in here with 0 rocks, right? Well, that's great as far as I'm concerned. That's something that, from a safe landing perspective, this would really help out. Alternatively, I could use this same technology if I had a cargo mission there that was transmitting. I could use this same technology to home in on a beacon and get near the cargo mission. Okay? Let me show you just a couple other quick concepts. These are different shapes that one might consider for human Mars exploration. I mentioned that these capsule shapes that have served us so well, may be kind of going out as we try to put more and more mass in. We're probably going to be going more towards these slender body shapes. It's possible that you would start to see some control surfaces on the vehicle, like the shuttle has a body flap as an example. And of course, here's my large inflatables that we're also interested in. These are the kinds of things that you will see in the future as we get closer to sending humans to Mars. From a heating perspective, there's some serious challenges out there. As the vehicles get larger, a couple of things happen. We run into a nasty thing called turbulent heating, which basically is an augmentation, a big increase in our heating, a hard thing for us to deal with. We also run into radiative heating, which we haven't been exposed to yet at Mars on our smaller vehicles. Both of those things are going to push us to entirely new thermal protection systems. And so there's going to have to be a lot of work done at NASA and elsewhere in developing advanced thermal protection systems. Just to give you an idea, if I had let's say a 15-meter diameter Apollo-like capsule or a CEV-like capsule, how would I make a heat shield out of that today? I can't make that all in one piece. I'm immediately going to have to go to some sort of segmented or tiled approach. It's going to look a little bit more like the shuttle heat shield than like the Apollo capsule kind of single monocoque heat shield. Well, all these seams and gaps are going to be big challenges, right? I got to get them all up. Maybe this is done, by the way, if this is 15 meters in diameter, I got to probably do some on-orbit assembly there. That means I got to certify these gaps and seams in space. I got to, in flight on the way to Mars, I got to check it out, do some validation, make sure those seams and gaps are okay before the big heat pulse. That's a challenge that needs to be looked at. When you get to packaging, now remember, inside this capsule has to be all your stuff for the surface mission, but also has to be all the stuff that you need to slow down still, right? We still need our supersonic decelerator to be packaged in here. We need our engines to be packaged in here. And so this is just a quick trade, assuming we needed about 1 meganewton of thrust. These engines have been sized to produce that thrust. And what you can see real quickly is the more engines you have, kind of the more volume the less volume you use for the propulsion system and the more volume there is for the payload. These are the kinds of trades that would have to be done. Additionally, the people have to fit in there, right? Or there has to be some other structure that is carried along, some inflatable habitat. Well, if you look at the established NASA guidelines for what it takes to send 6 people on a Mars mission, on a conjunction class Mars mission, they require, for optimal performance, 120 cubic meters of volume. By the way, that's not very much for 6 people. And the minimum allowable is 60 cubic meters. Well, these capsules, even a 15-meter diameter capsule only gives you a total enclosed volume of 290 cubic meters. At least half of that is going to be equipment, right? So we have a real challenge here from a habitable volume point of view. If we go with a smaller capsule, one that could be launched in one piece, maybe with a new launch vehicle, I'm assuming that the maximum size that the Ares 5 or some new launch vehicle could lift is about a 10-meter diameter. Well, then we're going to need a separate habitat for the flight from Earth to Mars. They're not going to be able to be in this capsule the whole time. And regardless of the size of the capsule, once the capsule gets down to the ground, we have a real issue with usable floor space, right? Think about how small that area really is. So maybe, once again, we might be talking about an inflatable habitat for the mission once again. And of course, on-orbit assembly does come into this. Now, last thing I want to cover real quick is we've been doing this kind of work at Georgia Tech with my students. It's been kind of fun. And this semester, our project was design and architecture to deliver a 20 metric ton payload, just the payload itself was 20 metric tons, to the surface of Mars. And I had 5 design teams of students at Tech that explored this. And the neat thing to me is the 5 teams, they all had the same class, they all had the same information. The 5 teams actually came up with 5 different approaches. And what that really tells me is we don't know the answer yet. There are options, but we don't know the answer. So this team had a slender body entry vehicle that did a direct entry. It didn't go into orbit first. It deployed, it dropped a lot of the slender body part, and then it inflated at Mach 5 a huge device, a 40-meter diameter supersonic decelerator, right? This is to solve the supersonic gap problem. And then this thing was big enough so that it got subsonic quickly and it could use propulsion to decelerate. It landed about 20 metric tons of payload, and at the top of the Mars atmosphere, it required about 80 metric tons. Here's another concept from my students. These guys used a 70-degree sphere cone that was very large, 12-meter diameter, so it would require either on-orbit assembly or some new launch vehicle. It went aero-captured, and then it did a direct entry, and its Mach 5 decelerator was smaller. You can see that here, it was smaller. And so it initiated its propulsion supersonically, as opposed to the other team that did subsonic propulsion. Which option is better? I don't know. Are they both viable? Yeah, on paper, yes. But there's a lot of work to be done in either case. And then what the teams did is they developed mass estimates for these things. And typically you could get about 23 or 25% payload mass fraction. That's the amount of payload delivered divided by the mass you started with at the top of the atmosphere. Okay, so let me summarize and take some questions because I'm going a little long. I apologize. The Mars atmosphere is our real challenge. Okay, if we both love it and hate it at the same time because of what it does to us. Today's robotic missions have been incredibly successful, but we're really reaching the end of the technology line that was started in Viking with the Mars Science Laboratory. We're not going to be able to get much above 1 metric ton with the technology solutions in hand. In my opinion, to date, there's been not a completely credible EDL architecture put forward that doesn't require some little miracle along the way. And the reason for this is because we haven't invested in technology. We're continuing to rely on the Viking era technology. Now, when we talk about humans to Mars, what's important to realize is that the human aerocapture and entry, descent, and landing systems of the future are going to have very little in common with these robotic missions. And so what we need to do is put together a significant technology and engineering investment program. These are a list of some of the technologies that I think are promising. There are, of course, others. This is just my opinion of some of the things that we could be investing in to allow us to one day send humans to Mars. And, I want to close by saying, I've been maybe I might come off a little negative. I'm not intending to. I actually believe this is possible. I just don't believe that with today's technology, it is possible. So if we make these investments, then we will be able to develop new architectural solutions and options that will allow us to effectively and efficiently send humans to Mars in the near future. Thank you very much. If there are any questions, I'd be glad to take them.
What is the speed of sound at sea level on Mars?
Yeah, it's a little over 200 meters per second.
Listen, have you ever considered landing humans with those big little balloons that blow them?
The airbags. Yeah, the MER and the Mars Pathfinder airbags. Yeah, so that's a very good example, actually. The answer is no. And the reason is that they are not scalable even to 1 metric ton. We looked hard at them for the Mars Science Laboratory, and they just don't make it compared to propulsion, right? So they're good for small robotic missions in rough terrain, but they're not. Not every solution works for every problem.
I have two questions. One is, how do you compensate for the seasonal variation in atmospheric density you're calculating on the Mars atmosphere? And I didn't see any wings descent vehicles, and I was wondering why that died out in the trade study.
Well, first of all, my trade study is ongoing. Well, let me talk about the atmosphere first. The atmosphere variations on Mars is a big deal. There are seasonal, daily, latitudinal, dust-driven variations in density and winds, and we understand them very poorly. Okay, so what we do is we design conservatively, and it basically makes these vehicles less efficient and bigger mass hogs than they need to be. The Mars Science Laboratory mission is being designed assuming there's a pretty large dust storm going on, it will still be able to land safely, just as one example. Okay, now, if we had, the Weather Channel at Mars, and maybe one day we will, then, and if we decided to go into orbit first, right, so that we could wait out some problems, then we could maybe take some of that conservatism out, and we'd get, maybe 5% back in our mass fraction.
Are these calculations done with the minimum seasonal atmosphere or an average?
Yeah, so the calculations that I showed were done for the missions, the robotic missions, with the actual atmospheres from those days. But when I do design studies, I use like a 3 sigma, basically conservative atmosphere. Yeah, like a minimum atmosphere. Now, your other question about wings, the reason you don't see any of my concepts, at least with wings, is that wings are heavy. And as I said when I was talking about lift to drag ratio, we need some lift, but we don't need, in my opinion, a lift to drag ratio of 1, like the space shuttle delivers. We need a lift to drag ratio of maybe a half. And you can get that with these slender body shapes just by flying angle of attack with a body flap for control. Okay? Yes, sir.
Yeah, I was noticing in some of your students' concepts that it was kind of a local minimum of altitude for max Q, and then you kind of increase in altitude. I was wondering what causes that. That's a unique characteristic of the flight profile. I'm wondering what.
Yeah. Okay. Well, those weren't real. Those are just single trajectories, right? But what happens as the mass goes up, you basically fall below equilibrium glide slope. Basically, the straight line path that you'd like to be able to achieve with lift to drag ratio. And so you end up using a guidance algorithm to basically fly around that, and so you get that type of motion. It's not a roller coaster or anything like that, and it can be controlled a little bit better than what was shown in those drawings. But it does do that as the mass goes up. Yeah, it's very observant. Yes, sir.
It's been a few years since I've read last Dr. Zuber's Mars Direct plan. I don't remember any very specific.
I think he actually has a pretty good plan. He's got a slender body aeroshell. He's got 2 of them, and they do rendezvous. That's all good. I do not think that in his studies that he's done the detailed work, particularly on this problem, to get to the depth required to say that it is, without doubt feasible. What he's done, in my mind, is like a lot of the DRM kind of work. It's a concept study. His particular concept, I think, is a good one. But the devil's in the details on this thing. Okay.
How difficult does it appear to be to do Mars orbital rendezvous?
Mars orbital rendezvous. You mean if you went into orbit and there was another vehicle there to
For instance, if you send propulsion
yeah.
fuel
No.
ahead,
Yeah, I don't believe that Mars orbital rendezvous is a huge challenge. In fact, I believe that in the robotic program for Mars sample return, we will demonstrate it fairly soon when we get around to doing that mission. Yes, it's not a we've already done it thing, but I don't think it rises to the challenges that I'm talking about here, because I don't think we need the same amount of technology investment to pull that one off.
well, I was wondering, was it part of the problem is you need so much fuel mass in the lower orbit
Mm-hmm.
to be able to get the kind of propulsion control landing. Why can't you put a lot of that in orbit in Mars ahead of time?
Well, you could, but you have to get it all there somehow. So you have to either get it there with propulsion, which is not a great gear ratio, or you have to get it there with aero assist. And then you have these same challenges. Okay, last one.
Yeah. As Apollo was winding down, Braun presented a plan to send humans to Mars, and in fact, the arrival date in 1981.
Yeah.
Do you think, I can guess the answer, do you think that realistically within the 10 years he gave himself, he would have worked out the mission?
Huh. Well, that's a great question, but that's...
He has 10 years.
What's that? Yeah, his 10 years. Yeah, I understand. Well, he, of course, had nuclear... His question was, Werner von Braun, at the end of the Apollo program, published his approach for going to Mars, and he was going to get there in 1981, which was about 10 years. Do I think that he could have achieved that? I think you got to realize at that time we had a very strong technology development program. The nuclear, his nuclear stuff was ongoing, and NASA was all about developing new technologies. In fact, at that time, a lot of these Viking era technologies came about. So the culture was a little different then, and I think it was focused on technology development. Had they turned their attention to that problem, as opposed to sending a robotic mission to Mars and building the shuttle, I do think that could have been possible. Maybe not in 81, but not that long afterwards. I think it's possible today, okay? I'm not saying that this is not possible. I believe it is possible to send humans to Mars, but what I think is needed is a significant 5 to 10 year technology development effort, like we had leading up to Apollo, like we had leading up to Viking. If we as a nation make that commitment, we can do this. All right, well, thank you very much for your time. I appreciate it.